hello everybody. So now let us continue our discussion further, and today we are going to cover in this week the applications of host case chemistry to different the class of molecules. So we are going to investigate now host case complexation behavior in podands, corands, parents to start with, and this will be followed by looking at other class of molecules. For example, we will be looking at cyclodextrins and the host guest behavior in these class of molecules as well. So let us start first by looking at what is a podand to start with. So to start with, a podand is written in the following way, where N is the number of repeating units, D is the donor atom, and this open chain conformation, the open chain conformation of this organic molecule is referred to as a podand. So it is characterized by an open chain conformation. Then we will look at other properties of podand also, but let us look at what are corands. Corands are the cyclic components of these open chain molecules. For example, we can now write it. We have the same set of donor atoms. We have this cyclic rings, and then N is the number of units which repeat. And donor atoms can be oxygen, NH, sulfur, and so on and so forth. So this constitutes what we called as corands, and when the donor atom is oxygen, this constitutes a special class of molecules which we call as crown ether, and we will be looking at the properties of crown ethers in more details. Now we have also realized that the pre-organization of the host is very important. So in this regard, this is a cyclic system, so this is more pre-organized and more rigid compared to a podand which has got an open conformation. And if you want to now pre-organize the host even more and make it more rigidified, then we can access the bicyclic compounds, which are essentially three-dimensional in nature and which we called cryptands. So let us look at how the cryptands look like. So here we have got B. B is referred to as a bridging atom. D is the donor atom, and you can see that the two B represent the bridged atoms, and then between these two bridges you can have the one ring which goes like this, the other like this, and the other like this. So this gives it a three-dimensional nature, a pre-organized host, and N is the number of repeating units here, and this class of molecules is referred to as cryptands. Now let us take some specific examples of podands. So, as we see that podant is characterized by open chain conformation. So, we can now write so we can have this particular podant which we call as the penta ethylene glycol dimethyl ether. Okay. So, we have the ethylene glycol units, these are the ethylene glycol units which are repeating, and there are 1, 2, 3, 4, 5 such units, and you can see that the methyl groups is present at the terminal part. So, this is referred to as the corresponding pentaethylene glycol dimethyl ether, and this you can see has got an open chain conformation. So, now if you put in a guest molecule, say if you add potassium cation, we know that this conformation has to wrap itself around the potassium cation, and that is going to be entropically unfavorable because we have got an open chain conformation, and now we are going to rigidify the host. So, we have got to restrict the conformation so that it can effectively encapsulate this potassium ion, and therefore, there is a entropy loss. There is also an enthalpy penalty here because this particular ligand is extensively solvated in aqueous solution, and now you will have to remove the solvent molecules, desolvate it, and then only it will undergo complexation with the potassium cation so that it can form this particular cyclic system. So, this is how the podant encapsulates the potassium cation. It wraps itself around the potassium cation and it forms this cyclic substrate. So, this wrapping process takes place, and therefore, there is a large entropy penalty as well as enthalpy penalty you pay because pre-organization has not taken place, and we have got a very open chain conformation, and hence the synthetic chemists now felt that we should modify the podant ligand to a certain extent so that we can rigidify the host to a certain extent, and this is done using the concept of end group concept, where we essentially anchor a bulky group at the end of the podant arm, at the end of the podant. So, at the end of the podant, particularly here, we can replace methyl by much more bulky substituents. For example, we can create so we have this 1, 2, 3, 4, 5 oxygen atoms, and now we can bring in a quinoline moiety which is having lot of steric bulk. So, when you bring in this kind of a quinoline moiety, then the podant gets pre-organized and rigid, and this will facilitate the encapsulation of different kind of cations. For example, you can have potassium ion, you can have uranyl ion. Say you start with uranyl nitrate salt and you can dissolve it in a solvent and or in aqueous solution, and it will form the uranyl ion, and the uranyl ion can also bind with this particular quinoline substrate. So, this kind of pre-organization using the end group concept is supposed to impart rigidity to the podant host, and we can also modify this further. For example, we can make benzoic acid substituted podands as well, and this kind of species can also now effectively encapsulate cations. Why? Because the hydrogens here are acidic. So in the presence of a base, I can form the acetate anion, the benzoate anion, and the benzoate anion can now participate in cation complexation along with the oxygen atoms as well. So you can have effective encapsulation now of this cation using the benzoate moiety as well as the three individual etheric oxygens. So with this background, we can now go and see the corresponding cyclic ethers, which are called corands. And in comparison to the acyclic host, it is the cyclic ethers which belong to the corand class of compounds, which got lot of recognition and has got very important applications. And these also are referred to as crown ethers. Now, the crown ethers are a very interesting class of molecules, and the discovery of crown ethers was done in 1987, for which the Nobel Prize in chemistry was given to Charles Pedersen. Charles Pedersen was a chemist who was working that time in an American company called DuPont, and he was synthesizing, he was trying to synthesize an organic molecule. We will look at it, and it was during the process of synthesis of a particular organic molecule that the accidental discovery of crown ethers took place. So this is referred to as serendipity in science, and serendipity in science plays a very important role because most of the notable discoveries have happened due to serendipity. So what he was trying to do is the following. In the presence of sodium hydroxide tertiary butanol and then the workup condition, he was trying to synthesize this particular compound. So what happens is that this is a dihydroxy compound. So one of the OH groups has been protonated. Has been protected. One of the pyrene groups has been protected, and then in the presence of a base, you generate the nucleophile, which then goes and attacks the electrophilic center. The anion chloride ion goes away. You form sodium chloride, and then in the second step, you have the deprotection step, where you actually deprotect the pyrene system to form the dihydroxy compound. But what happened? The starting material actually contained trace amount of the catechol. It contained a trace amount of the catechol. And because the catechol was present in the presence of these reaction conditions, it gave this particular product So it gave this particular product, which we call as the dibenzo 18 crown 6. So you can see that the number 18 signifies the size of the ring: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you can see it is an 18 membered ring which is formed here. The number 6 here refers to the number of oxygen atoms which are a part of the cyclic system: 1, 2, 3, 4, 5, 6. There are 6 etheric oxygens, and there are 2 phenyl rings. That is why it is referred to as a dibenzo system. And this particular compound was obtained during the course of the synthesis by only 0.4%. So even less than 1% of the product was the dibenzo 18 crown 6. And Peterson had remarkable synthetic skills, so he was able to isolate this dibenzo 18 crown 6 and then look at its properties. So this is how the serendipitous discovery of this class of molecules called crown ethers was done during the process of a chemical transformation, where the target compound was to make this particular organic ligand, because he wanted to complex it with the vanadal ion and make metal complexes, but he ended up getting this particular dibenzo 18 crown 6 as well, because the starting material had a small amount of impurity which is the catechol. So even trace amount of impurity can give you a side product which can have very interesting properties in addition to the ligand of interest. So what he observed was that the next thing was to look at the physical properties of crown ethers. So the observations which were made by Peterson are that the compound, that is the dibenzo 18 crown 6, dissolved sparingly in methanol, but solubility was highly enhanced when it was dissolved in alkali metal salts. And this is one of the most important observation, or one of the most important property of 18 crown 6, that it is sparingly soluble, but the moment you put it in an alkali metal salt like potassium chloride or potassium permanganate, then the solubility of the compound was enhanced manifold. And so this compound has a very unique property, that it is able to dissolve to a high extent in alkali metal salts. And so what he was thinking is that it is possible that the potassium cation has essentially fitted itself into the interior of the crown ether cavity. So we know that the crown ether has got a cyclic, it's a cyclic system. It has got a cavity here, and possibly the potassium ion has gone and fallen into this cavity. He actually proposed this statement saying that the potassium ion has actually fallen into the hole at the center of the molecule, and eventually this did turn out to be correct, because when the crystal structure of the complex of potassium ion with this ligand was done, it was observed that the potassium ion is complexed with the oxygen lone pairs. So now you see that here the oxygen lone pairs are pointing towards the interior of the cavity, because we know that the prerequisites for binding are that the host molecule should have donor atoms which are of a converging nature, and the guest molecule should have diverging binding sites. So in order to maximize the cation host interactions, the oxygen lone pairs point towards the interior. They point towards the interior of the cavity and are able to effectively encapsulate potassium. Secondly, potassium is also of the right size to sterically fit into the cavity which is created by this particular dibenzo 18 coran 6. So it is very, very specific to the size of the cation. If the size of the cation changes, for example, if it becomes smaller, then it is not a very effective complexation process. If it becomes larger, then the potassium ion will not be sitting in the center of the void. Most probably, if you have a larger size cation, then it will sit above the plane containing the 6 oxygen atoms. It will not be in the center. So this is a very nice example of a steric fit between the size of the cation and the void which is created by the ligand. So along the same lines, then what people did was that they made other crown ethers as well. For example, we can now look at other crown ethers. We can look at, for example, instead of the phenyl group, we can also have the dicyclohexyl group. We can also have the dicyclohexyl group. So you can see this is the cyclohexyl ring, this is the cyclohexyl ring, and this is the 18 crown 6. And because this is more organized and more rigid because of the stereochemical restriction at the cyclohexane system. So it has to maintain the stereochemistry at these 2 carbon atoms, therefore it is more conformationally rigid. It is a more conformationally rigid system. And if you want to actually include larger size cations, then you have to increase the number of donor atoms in the particular host. So then you can make larger sized crown ethers. For example, we can make so 1, 2, 3, 4, 5, 6, and we can make this 8 oxygen atom system. We can make 7 oxygen atom system. So we can make these larger size crown ethers so that we can accommodate larger size cations, for example, cesium and rubidium, etc. And you can also make smaller sized crown ethers. For example, you can make so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the 15 membered ring, and there are 5 oxygen atoms. So this is called the 15 crown 6, and this is more complementary to sodium cation. This is complementary to the sodium cation. So sodium cation being slightly smaller in size, it needs a slightly smaller size void, and therefore 15 crown 6 is able to provide the same efficiently. And then it is also important to keep in mind that this particular host here exists in different conformations. In principle, there are 5 different conformations the dicyclohexyl system exists in, and these are referred to as cis, syn, cis, cis, anti, cis, trans, syn, trans, trans, anti, trans, and cis trans. So these are the 5 independent conformations in which the dicyclohexyl moiety can exist. So the next thing is to actually compare now the binding constants. So we have looked at podands and we have looked at the cyclic ethers which we call as the corands, and now we can actually compare that given the metal cation, what is the magnitude of the binding constant which follows. So keeping this in mind, let us compare, for example, the magnitude of the binding constant between 18 crown 6 which is a cyclic ether, and the corresponding pentaethylene glycol unit, the PEG unit. So, we will now like to compare, let us go back. So, we have this particular moiety, the pentaethylene glycol, okay, which has got 1, 2, 3, 4, 5, 6 donor atoms, and we also have the crown ether 6, which has got 1, 2, which has got 1, 2, 3, 4, 5, 6, 6 donor atoms. So, in both the cases we have got 6 donor atoms, and we would like to compare the log K value. In this case, this is for the potassium ion, we would like to study the log K value, and the log K value is 6.08 for the 18 cron 6 compared to only 2.3 for the corresponding open chain conformation. So, right away this tells you that 18 cron 6 is very efficient in encapsulating the potassium cation compared to that of the polyethylene glycol variant, and this is because we have already studied this. This is because of the pre-organization of the ligand. The ligand is already effectively pre-organized, and it has got the converging binding sites, so it can effectively encapsulate potassium, and therefore resulting in a high magnitude of the binding constant with potassium ion. And then what people have done is they have tried to modify the ether further, so that they can enhance the magnitude of the binding constant. So, in this regard, people have synthesized a new class of molecules, which we called as lariat ether, where what is done is that to start with we have got a cyclic So, we have got this particular ligand, and this is the ether where we have got 4 oxygen atoms and 2 nitrogen atoms, so the 2 NH groups, and the binding constant log K is 2.04 for the potassium cation. So, then what the scientists thought is that can we enhance or increase the magnitude of the binding constant by modifying the NH group, and synthetically this is done by replacing the NH by NR, where R also has got donor atoms. So, if you do a chemical modification where you actually now put and now you have increased the number of donor atoms by 2. So, now you see the side chain, this is the side chain or the side arm has got a ligand which is of a flexible nature, but has got 2 donor atoms, and this is referred to as a lariat ether, and it also is referred to as this lariat ether is also this comes from the word lasso, where essentially in lasso we have got a rope which is tied up at the end with a circular kind of a loop. So, the circular loop represents this particular ring, and the linear part represents this. So, we have got a lasso where the rope part is the side arm and the circular part is this particular cyclic ring. And now what happens is that when you add a potassium cation, here, this side arm will change its conformation. So, if the side arm is actually flexible, it is moving around. Now, the moment you add the potassium cation, the side arm changes its conformation, folds itself, and then stabilizes the potassium ion by additional binding which is provided by these 2 donor atoms, So, we see what happens is that now there is a change in conformation of this system, such that now you have got potassium ion which is stabilized by we have this nitrogen. So, this represents the cyclic part, which already has got how many? 1, 2, 3, 4, 5, 6 donor atoms. So there are 5 here, this is 6, then 7, then 8. So now there are a total of 8 donor atoms which bind with this potassium ion. So this additional stability, there is an additional enthalpic stabilization which is provided by the 2 donor atoms which bind with the potassium cation, and this actually increases the magnitude of the log K to 4.8. So it's more than double now. The magnitude of the equilibrium constant is now more than double, keeping in mind the effect of the modification of the NH group by the side chain. So these kind of modifications can be done, which can actually enhance the magnitude of the binding constant. And we can also further modify the side chain by even replacing this hydrogen by an R group as well, and those are referred to as bibrachial ethers. These are referred to as bibrachial lariat ethers. So the bibrachial lariat ethers have both the NH groups replaced by the R group. So with this we come to the end of this lecture, and in the next lecture we will now look at the other class of ligands as well, which are the sperands as well as the cryptands. Thank you.